Roots and coefficients, the relationship between the two. So the relationship between the solutions to the equation, if you like, and the coefficients. Back in quadratics, we have already seen this idea. And you may remember, there's our general quadratic, and we said the sum of the roots was minus b on a, and the product of the roots was c on a. Cubic. So again, we make a the leading coefficient, and then go b, c, d, and so on. Now, if we stick to that sort of notation, something wonderful happens. The sum of the roots is still minus b on a, doesn't change. Now, here's where it's a little bit different. It's not so much the product of the roots, it's the sum of the roots when we take them two at a time. So all the possible pairings. So we're talking about a cubic, so we know there's three roots. Let's call them alpha, beta, and gamma. So if we pair them up, we could have alpha, beta, we could have alpha with gamma, or we could have beta with gamma. They're all the possibilities. But when we look at them two at a time, it's still c on a, just like the quadratic. If I look at all three in one hit, it now becomes minus d on a. Now that pattern is maintained for all polynomials. So if I now go to a quartic, as long as I keep the leading term as a, leading coefficient as a, and then go b, c, d, and however many I need, it will always be the same. Sum of the roots when I just take them one at a time, minus b on a. Two at a time, now there's six possibilities when I've got four solutions, will be c on a. All the possibilities when I take them three at a time, so there would be four of those, and that'll be minus d on a, but now we'll have a new one. If I look at all four at a time, it'll become e on a. Notice the alternating, minus, and so on. Now, quartics is about the limit that we go, but we could keep going. So let's generalise it. Any polynomial, as long as we make that leading coefficient a, and then just keep going down b, c, d, until we run out. The sum of the roots one at a time. So notation for that, there's our capital sigma, sum of, and I just put one root down. So I'm saying sum of the roots one at a time. So depending on how many we have, alpha plus beta plus gamma plus delta plus epsilon and so on, that will always be minus b on a. Two at a time will always be c on a. Three at a time will always be minus d on a. Four at a time would be e on a. Now, here's the wonderful thing. Remember back in the quadratic when we had to find alpha squared plus beta squared? That relationship that we saw, alpha plus beta all squared minus 2 alpha beta, that pattern also remains no matter how many roots you have. So sum of, let's say you said alpha squared plus beta squared plus gamma squared, so you've now got three roots. It would be alpha plus beta plus gamma all squared minus two lots of all the possibilities two at a time. So two lots of alpha beta plus beta gamma plus whatever one I haven't said, if you get what I mean. Let's play with one. So it's a cubic, the roots are alpha, beta and gamma. We're going to find the values of 4 alpha plus 4 beta plus 4 gamma minus 7 alpha, beta, gamma. Alpha plus beta plus gamma, 5 on 2. Don't actually need the two at a time for this one, but I'll find it because I noticed this is part A. There's probably going to be another part and I might use it in that. So minus 3 on 2, alpha, beta, gamma minus a half. So 4 lots of the 5 on 2 minus 7 lots of the minus a half. 27 on 2 is our answer. So you'll find the same sorts of questions as we had in the quadratics. It's just there's extra roots now. I mean, 1 on alpha plus 1 on beta was a common question. But now we see 1 on alpha plus 1 on beta plus 1 on gamma because we've got the extra root. We do it the same way. Oh, well, let's create an algebraic fraction. The denominator would be alpha, beta, gamma. Top of the fraction would become beta gamma plus alpha beta. So the sum of the roots 2 at a time, on sum of the roots 3 at a time. And we've worked those out. The minuses cancel, the 2's cancel, and I just end up with positive 3. Any of the notes?
Yeah.
No, it's pointing to it, saying... All right, let's try another one then. Alpha squared plus beta squared plus gamma squared is... So using what I just mentioned, I can rewrite that as alpha plus beta plus gamma all squared minus 2 lots of 2 at a time. Substituting in, we get 37 on 4. Alpha, beta, and gamma, they're the roots of this particular cubic. Find, now a bit of a gift question, the first one. And, oh, you see, a lot of people would have got it wrong. What do you reckon they would have put as the answer?
Minus 3.
Yeah, 3 or minus 3, yeah. Because there's no x squared term there. So b is actually 0. So what looked like quite an easy question actually had a little twist to it there. Okay. Alpha, beta, gamma. No trick to this one. That one is just minus 1. And then they asked the reciprocal question that particular year. So as we did before, turn it into an algebraic fraction, substitute in what we know. Notice the minus on a minus, which becomes, 2003 paper, a little bit more recent. Oh, this is more interesting. 2 of the roots are reciprocals of each other. Find the value of k. So instead of calling the roots alpha, beta, and gamma, I'm going to call them alpha, 1 on alpha, because 2 of the roots are the reciprocal of each other, and then I'll just call the third one beta. So, I've actually gone straight to the product of the roots, because if 2 of the roots are the reciprocal of each other, when I multiply them together, I'll get 1. So I can actually find that third root straight away. And it turns out to be negative 3. I now know minus 3 is a solution. So I now know minus 3 is a solution. So using the factor theorem, I can say polynomial minus 3 is 0 and just sub that into the polynomial. And from there, I can find k. K is 13. Of course, you could have used some of the roots to it. I mean, it still would have worked. But 2006, we're getting closer. Cubic, rx squared plus sx plus t, where r, s, and t are real numbers. We have zeros that are 1, alpha, and minus alpha. Find the value of r, the pirate letter, r. Okay? Well, the nice thing here is r is involved in the sum of the roots one at a time. And if 2 of my roots are alpha and minus alpha, when I add them together, thank you, we get 0. So 1 plus minus alpha is minus r, and the answer comes out quite nicely. R is, no, that one actually is a negative sign. R is negative 1. Next part of the question, find the value of s plus t. S plus t. Well, t is involved in the one that would be 3 at a time. S is involved in the one that would be 2 at a time. So I guess we'll find both of them. Let's see what happens. When I do them 2 at a time, I got 1 times alpha, 1 times minus alpha. They'll cancel. Then the other one will become alpha times minus alpha. So I know s is minus alpha squared. Let's do 3 at a time. 1 times minus alpha would be minus t. So t is alpha squared. So the value of s plus t,
0.
Yes, s plus t becomes 0. All right, playtime.